Well, good evening. Welcome to Space Oddities. Thank you for joining us on this glorious Tuesday evening, as it is here. Hope you're all well. Thank you all for being here. If this is your first time, welcome to Space Oddities. We hope that you'll stick around and become a regular viewer because you are most welcome. So I'm joined tonight by the usual suspects. Hello, Michael.
Hi there.
Hello, Daz.
Hello, nice to see everyone.
Hello, Roger.
Good evening.
Hello, Lou.
Greetings, Andy.
How is everybody? Okay?
Yeah, fine, thanks.
Thank you.
Good, jolly good. Well, what have we got for you tonight? Well, tonight we are going to be taking a look at galaxies, telling you lots of really useful things and interesting things about galaxies. And we will be carrying on the second part of this next week, but we'll talk to you more about that later in the show. Thank you all for your gallery contributions. We'll be getting onto the viewers gallery shortly. And we're very grateful, as always, for you sending in your wonderful images, because we do love them, and showing them to our viewers. And that's it, really. Don't forget that if you would like to support Space Oddities, you can do so by buying a T-shirt or a hoodie. And they are all available at the Space Oddities shop. And you should have just seen a... hasn't come up here. Why hasn't that worked? Okay, let's try that again. So... you can click the link that should have just appeared in the chat, and I hope it's just... Is that actually appeared? No, that doesn't appear to be working. Let me just try that again. That's very odd. Just let me try that. There we are. It's working now. There we are. So there's a link in the chat now for the Space Oddities shop, where you can get your lovely merchandise for the summer, in the case of the T-shirts, and further ahead in the case of the hoodies. So that's that. We'd like to thank you all for your donations and your support of the channel. It helps grease the wheels of industry, as it were, keeps everything on the road. So that's brilliant of you. So tonight we've got our usual features. There's no news tonight, because well, there hasn't really been that much in the news this week. I'm saving a couple of stories until next week. There is one image that I want to show you. Just give me a second, in relation to a story that came up this week, which is quite exciting. So just let me find that. And it concerns the Vera Rubin telescope, which we've talked about often on this channel. Here's the Vera Rubin telescope, which is the building is now complete in Chile on the left, and there is the world's biggest digital camera, clocking in at an amazing 37 gigapixels. It's the highest resolution, biggest digital camera ever made, and it's, as you can see, it's about the size of a small car. The news is that they've been doing initial testing, and they have, over 3 nights last week, acquired 500 images per night with the new Vera Rubin telescope. Now, the Vera Rubin telescope is a survey telescope that is going to completely photograph the sky of the southern hemisphere every 3 nights over a number of years. And the idea behind this is that it will be able to spot and automatically flag anything in the night sky that has changed. So this means asteroids moving, supernovae, all number of astronomical phenomena that change in the night sky that might otherwise be missed. And the Vera Rubin telescope hopes to deliver some brand new science and lots of interesting discoveries. So we're really thrilled that they've done the initial testing, or they're doing the initial testing. When it's operational, the telescope will take more than 2,000 images per night, representing 20 terabytes of data every night at this very high resolution of this incredible digital camera. And we're very thrilled that everything seems to be going well. First light on the telescope, the first observations are due to occur somewhere towards late summer. So by late summer, we should have some actual images to show you. And at the moment, they're just doing software testing. And there we are. So that's the news about the Vera Rubin telescope. So
a couple of points, Andy. Looking at those images, did it look like that they were turning the turntable with the cranes?
yes, it did.
And And also, can you imagine having to fit that lens cap on there every night
Oh,
or every morning?
well, we've seen the lens cap, and it's massive, obviously.
Huge.
So there we are. All right then. So what we're going to do first of all this afternoon is we're going to go over to Roger for his weekly look at the night sky and the weekly viewers gallery. So Roger, over to you.
Okay, thank you, Andy. So here we are for the 13th to the 19th of May. Working our way through, and we've just gone past the full moon previous day, so we're working our way back to the last quarter as the week progresses, which is all well and good. And we've got the Galaxy season still underway, with Leo and Virgo still dominating the southern skies, but we are now starting to get some of the summer constellations coming through, especially with the Milky Way coming up through from about 3 o'clock in the morning. We do have Mars still in the night sky, but obviously with it being quite a few months away from its closest position for viewing, it's going to be rather a small size to observe, but it is there still in Cancer, so all well and good for that. So oh, right, wrong one, and off we go through the week. So we do have the moon coming through, but fortunately for us, it's getting lower in the sky. So although it will be still quite bright, it will only be up for a few hours through the night. So not too bad. We do have, before sunrise, we still have Saturn, Neptune, Venus and Mercury coming up through, with probably just Venus being the most notable, unless you can spot Mercury, but it is quite close to the sun, so it will be a bit of a challenge. But we do have that, and that's all coming through. So it's quite interesting to see how that goes. So on to the exciting part of the gallery. We do have another good contribution from our regulars, which is what we will be seeing. We've got a lovely landscape here, which we've got from Lee, called Journey to the Centre of the Milky Way. And this was taking along a disused railway line in North Cornwall with his Canon 600D and his Samyang 14mm and Star Adventurer, and processing it in Sequator, processed it Cyril and Photoshop. And he also did some light painting, and he got a little meteor in his shot as well. And this is the result.
Oh, wow.
Look at that.
That's lovely.
And a nice little meteor on the right-hand side too.
It does make a difference, actually highlighting the foreground there. Gives you some to focus on. That meteor is fantastic. But yeah, so beautiful that is. That's lovely. Yeah. Well done, Lee.
Well done, Lee. Thank you.
Yeah, so that was round about about 4 o'clock in the morning there. But he's got some good clear skies to get that definition in the Milky Way. Most impressed. Lovely. Right, and we've got a hydrogen alpha image of the sun from Michael Murphy. And that was taken on the 9th, which was on Saturday-ish. And got some lovely activity there with the around the edges and on the surface as well.
See the filaments, that's what we were talking about last week.
Coming out.
That's what prominences look like when they're facing us.
Yes.
Fantastic. Look at that.
Lots of nice detail there. He did post one today, but I thought I'd keep that for next week. Otherwise, we'd have two different solar images. So
thanks, Mick. That's great.
So we've got a little quick picture from Ian of the moon on Sunday. I guess this is done with his phone. A very bright,
looks like Privet Lane
nighttime shot. So that was probably yeah. It's must have been quite late when he got it up at that angle, but probably around about midnight, I would guess.
The detail in the with the cars and the houses at the bottom, it looks sort of pointillist, doesn't it?
I was just thinking, actually, it looks like a scene out of Wallace and Gromit. I don't mean that derogatory, but it does. It just looks like something like out of Wrong Trousers or something. But yeah, it's a lovely image.
Right. Okay, so we've got some from Kenneth, who's been using the 2-meter telescope in Siding Springs in Australia, and this is M98 in Comer Berenices.
The one we were talking about last week, in fact.
That is incredible.
Yes, it's slightly modified image that he reprocessed.
That's wonderful, isn't it?
To get all the details coming through.
Is that just on the right-hand side, but just about on the centre line? You can see a small fuzz. Is that actually a companion, or is that in the distance?
I don't. Well, it might be some line of sight, but there is something there. Yes.
And we found out actually after last week's show that there's something very unusual about this particular galaxy. This particular galaxy is blue shifted. In other words, this galaxy, even though it's 50 million light years away, is moving towards us. And that is because it's orbiting the center of the Virgo cluster. And at the moment, its orbit is bringing it towards us. And it won't last, of course. It will go further around the cluster and then move away from us. But it's very unusual to find a galaxy at that distance actually moving towards us. But there we are. They've also found aluminium in the spiral arms of this galaxy, well, which is quite exciting, really. And so it's a bit of an unusual galaxy.
I think cosmological redshift doesn't kick in until maybe 15 megaparsecs, something like that. I think so. Anyhow.
Anyway,
well done.
Right.
Brilliant.
Onwards and upwards, and we've got one that was taken in Hawaii, which is also through the Liverpool telescopes, NGC 2905 in Leo.
Oh, look at that!
Oh, that's lovely. Look at the colour.
Interesting.
What extent?
Quite a few
to that
spirals
galaxy.
there,
Did I see on Hawaii the volcanoes erupted again?
Yes, it has.
Yeah.
A 600-foot lava fountain, would you believe?
That's a lovely spiral galaxy,
Right.
isn't it?
Beautiful, isn't it? Well done.
Right, and then we've got same telescope in Hawaii, but M66, and this is 90-second exposures on the red, green, and the blue.
Oh,
wow.
stunning, isn't it? Stunning.
Stunning.
Yeah.
So is that galaxy? It's hard to tell if it's a kind of very planar galaxy or perhaps it's been disrupted in its formation.
It looks like there's some disruption there, doesn't it?
Yeah.
Probably has been disrupted by something because the bar's still intact. You got two spirals. It looks wifty, doesn't it? It looks as though it's curled up at one end.
Yeah.
There may have been an interaction with something at some time. But that's nice.
Okay. And I think this is Kenneth's last one for this week on here. And this is NGC 3423.
Oh.
I think it must be quite a little one, sort of face on here. This one.
Lots of star formation going on, isn't there?
Yeah, lots of star formation.
Like little steady arms, aren't they?
They're quite tight as well, aren't they?
Like a little octopus. Yeah. Well done, Kenneth.
Thanks, Kenneth. That's great.
And we've got some and some solar images from me here. So this is on the 7th.
Wow.
Mm-hmm.
Beautiful.
And then
Just saying, Roger,
and the
on
other.
the left-hand image at the top where you've got that prominence, did you see the images where
Yes.
this came further around and it stretched down to, you can see a little prominence just below it, literally, but that was one whole prominence and it had dancing filaments actually inside it. Did you see those images?
Yeah. I had
Yeah,
seen
it's
something
absolutely
of that.
gorgeous.
Yes. Yeah. Right. And then there was this one a few days after. This is an inverted one, so you got a white sunspot rather than the black sunspot, just to give the prominence.
Wonderful, Roger.
Prominence is rather a bit more of a.
That certainly is.
Very good. And then there's just this one. That should be. And the last one he's got is from Kevin Earp, where he's got a plane flying in front of the moon. Now, according to this, it's flying from Malta to Manchester.
Airbus A321.
An A321.
Wow, that's stunning.
Whoa.
That is so cool. That is stunning.
There we go.
That is amazing, isn't it?
Brilliant.
Absolutely amazing.
I'd just like to know whether that was serendipitous
Yeah.
or did he plan it. But that is so stunning.
Yeah, and that is the final image
Yeah.
from the gallery.
Kenneth says, thanks, guys. Been challenging processing the data, but sure, fun and great learning. Fantastic. And Ian says, pointillist Wallace and Gromit, he'll take that and run. Yeah, so there we are. Okay,
Well
thanks,
done, Ian.
guys. Is that's it, isn't it? Yeah. So anyway, thank you all for your
Yes.
images yet again, and keep them coming in because they're wonderful, as you can see, and we do love bringing them to you. If you want to send your images in to feature in our weekly gallery, then please attach them to an email and mail them to gallery@spaceoddities.space. That's all you need to do, and you don't need to put anything special in the subject or anything. Just send them to gallery@spaceoddities.space. And not only do they appear in the weekly gallery, you also get your own gallery on the Space Oddities website, which is https://spaceoddities.space, easy to remember. And you can build up your own little gallery there with which you can absolutely stun, amaze, and shock your friends and family. And great, and we're really happy to have those galleries on the website because we love looking through them. Yes, Anne says great images. Thank you, Anne. And Paul says, well done, everyone. Beautiful, stunning images. Thank you, everyone, for sharing them with us. Indeed, here. And there we are. We have a very high standard among the people who submit images to our gallery, and we've never rejected any images at all that have been sent to us. So the standard is high. So keep them coming, and thank you. Okay, so we're going to move on now, and we're going to go through the first bit of our theme for this week, which is galaxies. Now, we've just seen many photos of galaxies, and galaxies, of course, are the cities of the universe, conglomerations of stars. Daz is now going to tell you exactly how they're classified, because they can come in all sorts of weird and wonderful shapes and configurations. After that, I'll be telling you about the galactic hierarchy, about how they're organized in terms of organization. How are they organized in groups, and what does that mean in terms of the universe? And there we are. So I think Daz is ready to do that. Okay. So
can everyone see that?
Yeah, that's fine.
Right, that's okay. Now, what I'm going to be talking about today is visual classification. I won't be going into things about too much about black holes at the centers, whether they got jets or anything like that. I'm just going to talk about the galaxies as they look visually when we take images of them. So here we go. Right, basically, first of all, what is a galaxy? Simply put, it's a large galaxy consists of thousands of star clusters and billions to trillions of individual stars, all held together by gravity. The Milky Way fits the bill as a large spiral system, which we'll talk about soon. But galaxies come in many shapes and sizes. The main types are elliptical, lenticular, spiral, barred spiral, irregular, and low surface brightness, which we'll be talking about in a while. Right, so okay, then, just a matter of interest. Can you see my cursor?
Move it
No?
around.
I'm moving it, so no, obviously not. So I'm going to have to. So basically, we've all seen this before, hopefully, and this is what is known as a Hubble's tuning fork. Back in 1926, when Hubble was doing his observations, he decided that really we needed some way of classifying the galaxies more by their shapes. So basically, what he did is he went through, and of course, we're talking about glass plates at this time. All the images were on glass plates, and basically, he was looking at the shape and the size, what characteristics you can see on the actual plate. So remember, this is a two-dimensional image of a three-dimensional object. So we're only seeing 2 dimensions rather than the 3, the whole view of the thing. Now, if you look at this chart on the side here, at the far left, which is E0, as it says there, you will find your elliptic galaxies. And I'll explain a little bit in what they are. As you move towards the center, towards the SO, you then come into your lenticulars, your lenticular galaxies. Then what you come is you come to spiral galaxies, and there's 2 branches of spiral galaxies. You've got your spiral galaxies at the top, and then the bottom fork actually is barred spiral galaxies. You will also see that they are labeled SA and SB, SBA, SB, SBBBA, and all this sort of thing. I'll just explain what those are. But what you're looking at is you're looking at the top with galaxies with no bar at the center. And then we've got galaxies at the bottom which have definite but distinct bars. So here we go. So what we have here, now this is a elliptic galaxy. Now what we're looking for here, what describes an elliptic galaxy, is you can see it's very diffuse, it's very fuzzy. And what we're looking for is we're looking for smooth features. We've got the center core at the center, but it's surrounded by all its stars, but they're smooth. There's no clumping. There's no star formation going on. And so the actually so it's basically a featureless light distribution, and it can appear as ellipses. Approximately round when they're face on, and elliptical when they're edge on. So that's what we're looking for. We'll go through a few of these images, and you'll see what we actually mean. So, right, here we go. Now this is an edge on elliptic galaxy. As you can see, you've still got the center core. You've got the massive stars around. I know you can't see my cursor, but I am moving around. You can see it's surrounded by stars, and we're on an elliptic here. You can see it's more side on, so it's given us sort of more of an egg shape rather than an extended sort of like rugby ball shape. So these are your elliptic galaxies. Then we move on. Here again is another elliptic galaxy. And I'll put them at the bottom, their numbers, and also where you can find them if you want to go and look at these. So there's another, this is Messier 60. So, and here's another one. Now this is Messier 87. Now this, as I said, this is visual, and of course we all know this galaxy because it's the one the Event Horizon took an image of the black hole, or rather, it actually took an image of the shadow of the black hole and its surrounding um, disk. So that's why we always remember this one. And of course, we also know that there's some quite large jets following off of this one. So again, that's an elliptical galaxy because you can see center core. You can actually see part of the one of the jets there as well at the top, the sort of like the 1 o'clock things there. But the rest of it's all fuzzy. So again, here's an elliptic. We're almost getting on the verge of a lectinier, but I'll tell you exactly. Now, this is a lectinier galaxy. You can see there's a definite disk around it. You can see there's definitely dust. There's a good chance that there's possibly clumping on there, but it's also got a central bulge. So that's what we're actually looking for. So we're looking basically for like an egg shape, a saucer shape type thing. So again, it's a long elliptical galaxy. It's stretched out because we're seeing it side on. So this is when it becomes lectinier. So you can see the dust. And this is NGC 5866 in Draco. If you want to go and have a look at that at any time. So again, here's this is an elliptic galaxy. On it, if you look at it on the right, but then when we look at it in different wavelengths, you can see it's actually a spiral. So again, this is what I said, we're talking about visualization. So if you looked at it on the right hand side, you'll say that's an elliptic galaxy. It's very smooth. We've got a central core, but there's no clumping. But then when you look at it in different wavelengths, there is definitely a structure there, and you can see some clumping. So it's a lectinier sort of or elliptical galaxy. People, people debate these things because it's what we're looking at. It's what we're seeing on the plate. So it's, again, as I said, you've got to be remind yourself that this is the time. Again, this is a Messier 86 in Virgo. Again, you've got some lectinier shape. You can see that in the center there is a small rugby ball shape in there, but it's in a diffused set of stars. So again, elliptical, lectivular. I'll get that word right in a minute. So we'll go on. Again, this is now this one is a barred lectivular galaxy, and this is basically we're seeing it at an angle. It's not face on and it's not side on, but you can definitely see that there's a small bar in there, and you can see a spiral structure in there. So this is a lenticular galaxy. So again, because again, when you look at these things, you can either see them face on, you can see them side on, or you can see in some degree in between. And this is this is basically why they decided that they had to sort of try and classify these things. But again, everybody else sees something different, so they do tend to get classed between one or two classifications. Again, this is in Centaurus. This is NGC 5128. And it's an elliptical galaxy again, because we're looking side on. Look at those dust lanes. It looks as though this possibly had some interaction that's happened with it, but you've got your center bulge, so you've got your clumping and stuff like that. So we're looking at it side on, but yeah. Right, now we're looking at spiral galaxies. Now here I've got both types. On the left, you've got a spiral galaxy devoid of a bar, but you can see you've got your central core, and then you coming from the core, you've got these spirals. Now, usually you only get two, but as you can see here, you've probably got 3 or 4 coming off of this. So that is just described as a spiral galaxy. And this is NGC 5453, 557. So it's basically the pinwheel galaxy. And then on the right-hand side, you've got a barbed spiral. So you've got your central bulge. Then you can see you've got sort of like this rugby ball shape, but it definitely inside of this rugby ball shape, you can see two definite bars. So the bar can either appear as this rugby ball shape, or you can actually see a definite bar shape. You've got it both here. And then at the ends of the bars, you've got the spirals coming off on each one. So this one's got two spirals. One spiral actually splits into two a bit further on. But this is NGC 130. So this is the two charts. So you got on the left spiral, then you got the barbed spiral. Right, this is what I meant about the classification within the spirals. Now, if you look at the actual side on the left-hand side, it'll say SA, which is a spiral galaxy, and then it'll say SBA, which is the barred spiral galaxy, followed by an A, B, or C. The B on the barred spiral is made capital because, as you can see, in the galaxy region, you've got an SB. And basically, what these are doing is they are telling you what you're actually looking for it to fall into one of these categories. So SA is tight wound, smooth arms, large, bright central bulge. The SB is less tightly wound spiral arms than an SA, but somewhat fainter bulge. An SC, loosely wound spiral arms, clearly resolved into individual stellar clusters and nebulae, smaller, fainter bulge. So this is the classifications that actually then for the spiral galaxies fall into. So again, it'll either be under the spiral galaxies, or it'll be the barred spiral. But the classification letter will always remain a small letter, and that tells you basically what you should be looking at. And as I said, this is all. Everybody's got a different perspective on this, so no people will probably see the same galaxy as the same classification. So here we go. Here we are. This is Andromeda. We all know this one. This one's coming towards us again, and we're due to collide with the Milky Way in a very well in the far distance. But again, it says here it's a barred spiral galaxy, and it, like I said, it's similar to the nearest to the Milky Way. So that's one of the closest spiral galaxies we've got. Messier 74, again, is known as the Phantom Galaxy. And again, it's a large spiral. You can see there's no real defined bar in there. So again, here we are. This is the Grand Design Spiral, known as the Grand Design Spiral Galaxy. It's Messier 81 or Bode's Galaxy. And again, you can see no definite bar in the center there, but you can definitely see the spiral arms. Again, this is more side on. This is the Sombrero Galaxy. Again, you've got, as you can see, it's got a smaller bulge. It's a bit fainter, but you can still see that there's definite detail in the form of the spirals actually on the in the disk, because again it's just slightly tilted towards us, and what we've got, the dark line on the edges, is the dust lane that's actually facing more towards us. But again, you can definitely see it's a spiral. Whether or not it's got a bar, I don't think it says. No, it doesn't say on there. So again, here's another spiral galaxy, the Whirlpool. We all know this one. So it's one definitely the big one is a spiral galaxy. The other one's getting a little bit messed up because it's interacting, and you can see the star bridge that's actually joining them. So we all know the spiral, the Whirlpool galaxy. So again, here's another spiral galaxy. There is a very small bar in the center. But it's a bit distant. But this is NGC 300. But you can also see there's some star forming. There's some clumping of stars. There's some star forming going on. And this one is in the constellation of the Sculptor. Right, again, here's another one, definite bar in the center. But some of these images are absolutely fantastic, and you can also see on as well as in the actual spirals, you can see the star forming going on. Look at the halo as well outside. There is definitely star formation going on in the halo, so there's something's to perturb that at some time, and with the pressure waves that have been caused by it, you've definitely got star forming going on even in the outer reaches of this galaxy, but it's a barred spiral. Again, here's another definite bar spiral. You can see the big rugby ball shape in the middle. You can definitely see part of the bar, and again the actual spiral arms start at the end of the bar. So, and well, this one you just cannot miss. You've definitely got two bars, and then you've got all the spiral arms, which seem to be now. This one I just want to quickly talk about. It looks like you've got almost two rings of interaction going on, and you've got the center bulge. There's a small ring. You can see a bar coming through, and then you've got the larger outer ring. Now, bear that in mind for another type of galaxy that I'm going to show you in a little while. So there we go. Yeah, and another one with really defined bars and the spirals coming off at the far end. Lots of star formation going on there. And you can see the very large rugby ball shape. So I'm just quickly going through these. Again, another barred spiral. You should be able to now notice the arms and the spirals that are coming off of it. So you can see what the difference basically. And again, another barb spiral. This is NGC 1672 in Dorado. Right, and this is more of a side-on one. This is called the Silver Coin Galaxy. But again, you can see there's definite clumping going on. There's a very small, not so bright bulge. But as you can see, there is definitely spiral arms embedded in this galaxy. I didn't realize I had this many on there. Again, another barred spiral. You can see the definite bar. You can see this is a two-arm spiral. This one's in Leo. Surprise, surprise. And then we've just come onto irregular galaxies. Now, if you remember on the tuning fork, there was no fork for irregular galaxies. Because again, remember what we were looking at was galaxies that could be identified on glass plates, a two-dimensional object, image of a three-dimensional thing. So basically, when Hubble did his, he had no intention of putting irregular galaxies on there. But in future versions to come, later on versions, people actually introduced irregular galaxies, and usually they put a fork coming from the center line and going straight out, and then at the end there they put irregular galaxies. Now, irregular galaxies are usually sort of like dwarf galaxies. They have no distinct shape, and they usually have got lots of star forming going on within them, but they also tend to lack a bulge. They do break down into two different categories, but I'll just quickly flick through these but you'll see that there is no defined shape there. That this has usually been caused by some previous interaction that probably has had another interaction with a galaxy that's moved on, and it's left this basically in quite a bit of a mess. So here are the three versions. One IRR1, which is a regular galaxy, is an irregular galaxy that features some structure, but not enough to place it cleanly into the Hubble sequence. Subtypes with some with spiral structure called SM galaxies. Subtypes without spiral structure are called IM galaxies. IRR2 are a regular galaxy that does not appear to feature any structure that can place them into the Hubble sequence. And then you've got the DL galaxy, which is a dwarf irregular galaxy this type of galaxy is now thought to be important to understand the overall evolution of galaxies, as they tend to have low-level metallicity and relatively high levels of gas, and are thought to be similar to the earliest galaxies that populated the universe. But we'll talk a little bit about that in a second. So let's have a look at some of these irregular galaxies. You can see seems to be no actual form. Basically, you couldn't distinguish that from whether or not it was originally a spiral, an elliptic, or whatever. And so basically, they had to be added to themselves. Again, here you've got one here that looked as though it seems to have an oval shape in the center, so it could be some sort of disk. But the rest of it looks as though something's passed through it, and it's literally splattered the whole thing. But it can't fit in the actual fitting of the Hubble Hubble fork. So I was going to say Space Telescope there. Again, another mishmash. So again, you couldn't put that into what we were looking at. And then we got what we call ARP galaxies. Now these ARPs, it says here, the ARP classification of galaxies primarily documented by Holton Arp's Atlas of Peculiar Galaxies focuses on galaxies that deviate from the typical Hubble classification of spirals, ellipticals, and irregulars. ARP's classification system aims to categorize galaxies based on their unusual shapes and features, often resulting from interactions with other galaxies or other phenomena. So let's have a look. Now here is a montage of ARP galaxies. And as you can see, most of them are galaxies that are actually either going through the process, and it's going back to the irregulars as well. The irregulars are usually thought to have been created as they are now by interactions with other collisions with galaxies. And these ARPs, you can't really fit them into the Hubble fork. So these have been given an ARP designation. They've also got NGC numbers and M numbers, but you can see what's happening here. You've got galaxies interacting with each other. Some of them you'll recognize. And and this is what will end up that some of them will pass through each other several times. And then you can either end up with a diffused elliptical galaxy far in the future, or to begin with, an irregular galaxy with a total mishmash. So that's ARP galaxies. Now, the other thing I wanted to talk about is that this, I've got to remind you again, this has flaws, only in the way that people use it. As I said, this is a visual only classification. Two-dimensional images of three-dimensional objects. So all that Mr. Hubble was trying to do, and he did warn people that this is how it should be read. If you make any inferences of otherwise, then that be it on your own head. You'll have to substantiate them, because he takes no responsibility for what you're saying. But basically, you can see here, these are all the images, two-dimensional images of three-dimensional objects. Now, some people also assume that this is an evolution map. And they have said to read it from left to right. So they're saying the elliptics and the lenticulars and the irregulars are what they call the, now let me get this right, the earliest galaxies. They call them the early galaxies. And then the spirals, no, sorry, I'm wrong. The late galaxies, and then the spirals were the early galaxies. I'm sure I'm getting that right. So they're saying it's an evolution, and that they're reading it from left to right, and that's how these things are going to form. Well, that's not true. As I said, this is visual only. It's got nothing to. But of course, you've also then got to, once you've done this clarification, you've then got to start talking about what the actual galaxies consist of. Now, when I was thinking about that previous galaxy, and I said that there's two rings, this is a ring galaxy. Now, this is called the Hogue's galaxy object. And as you can see, it's a galaxy with a central core, then there's a gap, and then you've got the ring of stars. And you can see what I've done here. I've forgotten to enlarge the picture. Sorry about that. But you can see a definite ring of stars with a definite gap in between. Now, there are some of these galaxies, also these ring galaxies, where there is no central bulge, there is no central core. There's just a hole all the way through. And these are thought to have been caused by something punching through the center of the galaxy, taking away the core and everything, and just leaving a ring of stars. But on this one, they also seem to think that some star forming happened in the center, in the core, which has pushed the stars into a ring, but also the pressure waves from what's happening in the core is then ignited star formation in the ring around the outside. So you get this sort of image. So and then we come to what we call ultra diffuse galaxies. I think that's what it says. I've got a thing stuck in front of it. Now, ultra diffuse galaxies, as you can see, there's, well, you can see no core. You can just see, all you can see is a definite blur. Now, the thing is, there are a category of galaxies that this will fall into. And you've got ultra diffuse, which is what these are, but they're also known as dark galaxies, which is what it's called here. There is also a classification of galaxies that have no dark matter in them at all, which appear like this. They're very diffuse, very spread out. And then you've got what they call low surface brightness galaxies. Now, these are a bit, they're in a sort of a category of their own. Some of them, when they look at them and they analyze them, appear to have zero dark matter in them at all. Yet others appear to have over 95% of dark matter making up the galaxy itself. So as well as that, so basically the actual matter we've got there, it is what we're seeing, but the majority of what we can't see and we can't measure is dark matter. But they're estimating that there could be up to 95% or more in these galaxies. So here's another one. Again, another one I forgot to enlarge. So this one, this has been taken by the Dragonfly telephoto array. Again, you can see it's just a blob. It's just, there's virtually hardly anything there. And it must have taken quite a bit of exposure to actually be able to pick these things up. So, and here we are. Here are two more galaxies. Again, their brightness is very low. Again, on the right-hand side, you can see it looks as though it's got no bulge in the center. There's no center core. But on the left, you can see it's spread out. It's more a bit of like an elliptic, but its light production is very, very low. And these have obviously been enhanced. Now, this is a theorized galaxy. And this is what they call the dark galaxies. And what it is they have found these sort of things. And what they're the thinking behind them is that they're basically, they call them primordial galaxies. And they're basically just gas, massive balls of hydrogen gas. Is it because they've got zero dark matter in them that they're not actually collapsing and forming stars? Because there seems to be no stars in this at all. On this one, this image here, now again, this is all theorized. This one is spinning. And how do we know that? We go back to Andy's red and blue shift. At the top, you can see it's actually red. And at the bottom, you can see it's blue. So it's actually, the bottom is coming towards us while the top is going away. So this is actually spinning like a galaxy. So for all intents and purposes, it's behaving like a galaxy. It's spinning. But it obviously, for some unknown reason, it started no star formation at all. Again, remember, this is all observational. This is a theoretical to actually call it a dark primordial galaxy. But this is theorized. But as I said, there's lots of things out there that I haven't touched on. But this was just basically a guide on visual classification. So I think that's it. Yeah, so that's it then. So we'll come off of there. We'll come back
Great.
to the
Thank you very
studio.
much, Daz. That's great.
Sorry if I waffled.
Don't worry. So yeah, thanks very much for that very useful guide to the classification of galaxies. We're going to move on now to talk about not the classification of galaxies, but the distribution in the universe, because there is a hierarchy in galaxy structures. So just let me talk about that. Just give me 1 second and we will have a look. Right, there we are. Okay, so let's first of all talk about our galaxy, the Milky Way galaxy. So it's a good place to start. So as Daz was saying, our galaxy fairly recently actually was found to be a barred spiral. It has that bar through the middle, as Daz said, the sort of the rugby ball shape, and those spiral arms emanating from either end of the bar in the middle. And our galaxy is
Andy,
about
are
100,000.
you showing images? Sorry.
Are you not seeing anything?
It's got nothing on the screen. No.
Oh, okay. Just give me a second then. What's going on with that?
Sorry to interrupt.
That's okay. It didn't share for some reason. I'm having a few technical problems. Okay.
You jumped off. Did it clear them?
No, shouldn't have done.
Oh no, there it is. We got it now. Yeah, we got it now.
Okay. So yeah, so this is ours is a barred spiral galaxy of the type Daz talks about, and as I said, this was discovered actually fairly recently, only about 15 years ago, I think, something like that. That our galaxy is indeed a barred spiral. It's difficult to work out the shape of our galaxy, of course, because we're inside it, and it's like being in one room of a house and trying to work out what the rest of the house looks like without going outside the room. So we know that our galaxy has somewhere between 100 and 400 billion stars, again for the same reason that it's difficult to work out exact is in our galaxy because we're inside it. But estimates do vary between about 100 and 400 billion stars. It's almost certainly somewhere in there. But our galaxy is fairly typical as a spiral galaxy. There's nothing incredibly different about it. It has its own peculiarities, but no more than any other spiral galaxies, its own distinct features. Now, where are we in this galaxy? Well, we're there, roughly, and that red circle there is where we are. Also, all the night sky, all the stars that you see in the night sky, all the stars you see in the night sky are within that red circle. So as you can see, our night sky, we're only seeing a tiny, tiny part of all of the stars in the galaxy. Now, when it comes to moving up in the hierarchy, our galaxy is part of a group of galaxies, but we will come on to that in a second, because before we get to the other members of the group, I just want to talk about the galaxies that are called satellite galaxies of the Milky Way. Here we have the small Magellanic Cloud on the left and the large Magellanic Cloud on the right. But there are other types of galaxy orbiting, as satellites of the Milky Way. I'll come back to why I said that in a moment. We also have things like the Sagittarius dwarf galaxy, which is a dwarf galaxy that is moving around at quite a distance from our galaxy, but it is going around it. And in the process, the gravity of the galaxy is tearing this dwarf galaxy apart, leaving behind it a trail of stars called a tidal stream. And we see these in other galaxies, so it's nothing atypical. But this is a fairly common feature of galaxies. When galaxies get too close to the disk of the galaxy, then they tend to get torn apart, as shown here by the the Sagittarius, excuse me, the Sagittarius dwarf galaxy. But we also have other dwarf galaxies around the Milky Way. They are known as spheroid dwarf galaxies because of their shape. And there are more or less about between 20 and 25 of these around the Milky Way. And there's the plane of the Milky Way in the middle, and obviously the supermassive black hole Sagittarius A star at the center. But it's not quite as simple as that, because for many years, forever basically, since all of these galaxies around the Milky Way are discovered, most of them are dwarf galaxies. And what has now been discovered by Gaia, Europe's fantastic spacecraft that unfortunately recently ceased operations, but which has been mapping billions of stars in our galaxy, Gaia has made a bit of a shock discovery about all of those dwarf galaxies. They're not actually orbiting the Milky Way at all. Most of them are approaching the Milky Way galaxy from outside the galaxy for the first time. So they're not satellite galaxies of the Milky Way. They're not orbiting it. They are moving towards it. In particular, the Large Magellanic Cloud, thanks to Gaia's exquisite measuring precision, has been shown to have a position and a trajectory and a velocity that means it can't possibly be orbiting the Milky Way galaxy. And the same for most of the other dwarf galaxies. It might apply to all of the dwarf galaxies once all the Gaia data has been analyzed, which it hasn't been yet. So this is something that has really put the cat among the pigeons in terms of our image of what or our view of what the Milky Way is like. Those galaxies around it are approaching it, not orbiting it, according to the latest Gaia data. So we move up from our single Milky Way galaxy to a group of galaxies called the local group. And this comprises between 20 and 30 galaxies in a group held together by their mutual gravitational attraction. And we have such famous galaxies as the Triangulum Galaxy, the Andromeda Galaxy, of course, which is moving towards us, as we know, and will merge with the Milky Way in 4 or 5 billion years' time. And this is known as the local group, about 20-25 galaxies in a group. Now, galaxies in a group are very common. All galaxies, in fact, that we know of belong to some sort of grouping, but this is not the end of the hierarchy. Let me show you where we go from there. So there's the local group in the center of this image. We have other groups at varying distances from the local group. The Virgo cluster is the biggest of these, at about 65 million light years away. And you can see all the arrows pointing in different directions. We've got the M66 group at 35 million light years away, Leo 1 at 38, the M81 group of galaxies, 11 million light years away, the Ursa Major group, 55 million, and so on and so forth. So this is moving up the hierarchy with lots of these groups of galaxies. Now together, the galaxies in the Virgo cluster comprise about 200 galaxies. Most of the galaxies in the Virgo cluster are dwarf galaxies. And I don't know whether you can see bottom right, there's a classification of the ones on this graphic into elliptical, lenticular, spiral, and irregular, as Daz was saying, but that's not really important. The point is that this is the biggest cluster closest to the local group in terms of its size. And then we move up again, up to something called the Laniakea supercluster. Now, the Laniakea supercluster is a huge cluster that includes other clusters of galaxies. Now, just to remind you where we are, put that up there, here's the local group of galaxies. Over here is the Virgo cluster of galaxies, but as you can see, there are lots of groups and clusters of galaxies. And we've got the Centaurus cluster to the right. We've got lots and lots of different groups of galaxies together forming clusters of galaxies and then superclusters of galaxies. And the Laniakea supercluster comprises all of these galaxies. And I want to tell you a little bit more about the Laniakea supercluster, because it is an immense structure. Now, this looks a bit strange, but let me explain it. Basically, the orange line around this whole area is the extent of the cluster, and in total, it's about 520 million light years across. Now, in this graphic, all of the little white dots are individual galaxies. But also the lines in this graphic represent movement and direction through this immense supercluster. So you can see that the lines in white are movements towards the center of the Laniakea supercluster, and the blue lines are movement away from the gravitational center, the gravitational well, if you like, of the Laniakea supercluster. And this whole region contains the mass of about 100 million billion stars. So this is an enormous structure. But the Laniakea supercluster is not the only supercluster in the universe. There are more, but this is, if you like, our local one, the one we're actually inside, that comprises all of those groups and clusters and superclusters, and it's an immense structure. Where do we go from there in the hierarchy? Well, if we think of the Laniakea supercluster as just one supercluster, the only way we can go is up from there, and we move up to the cosmic web. Now, here's a graphic representing the cosmic web. And I just want to tell you about the cosmic web and what it comprises. So the cosmic web has these key features. First of all, it has the filaments that you can see in the image. These are long thread-like structures that connect regions of high density in the universe. The cosmic web has sheets, which are large, thin structures where matter is distributed in a plane. Then we have the voids. These are empty spaces between the filaments and sheets where there is relatively little matter, and you can see those are the dark areas in the cosmic web. There's hardly any matter at all within those voids, and some of these voids are absolutely immense. What else have we got? The nodes. These are regions where filaments intersect. You can see the nodes there in the graphic, and these represent high densities of matter, including galaxy clusters, and these where they are found. And lastly, we have dark matter. The cosmic web is primarily composed of dark matter, which is invisible but exerts gravitational influence and shapes the structure of the web. So as we now know, dark matter is incredibly important in the universe because it really does shape everything that we see and all the structures that I've talked about. So there you are. So that's the hierarchy of galaxies, how they form into groups and clusters and superclusters, and there you are. And that's about it. So yes, Lou is, as always, saying if dark matter exists. So there we are. Paul says, always thought they were satellite galaxies, just shows how things could be misinterpreted without good science data. Absolutely true, Paul. So yes, we now know that they're not satellite galaxies. And we've no reason to think really that when we look at, for example, the dwarf galaxies surrounding the Andromeda galaxy, because there are quite a few, I think there are a lot more than we found around the Milky Way. There's perhaps no reason to think that they are satellite galaxies either. Ian says, but the universe is infinite, there is no end, surely. Well, yeah, but that's not really the question. The question is, how is the matter in the universe organized? Whether the universe is infinite, of course, is very much up for question. So there we are. Okay, so where do we go from there? Well, where we go from there is Lou, because Lou's going to tell us about measuring all of this, aren't you, Lou?
I am.
Okay.
This is your modified Newtonian dynamics enthusiast talking to you from SpaceOddities.
We are going to have a debate about this at some point.
Yes, we should. Yes, we should. I will look forward to that.
Yes.
So, so we have all these galaxies, all these different types of galaxies, these different distributions of galaxies. They're everywhere. I just bring up a couple of pictures here. This image on the left is a Hubble Space Telescope image taken with its wide field camera 3 of about 10,000 galaxies, going back perhaps to 400 to 800 million years after the Big Bang, and it has took about 11 days to collect all this light. This piece of sky is about as big as the head of a pin held at arm's length. 10,000 galaxies. The image on the right is from James Webb Space Telescope. This is the James Webb Advanced Deep Extragalactic Survey image of 45,000 galaxies taken with their NIRCam, the near-infrared camera. And these galaxies may date back to about 600 million years after the Big Bang. And this is a 5-day integration. If you sit on these places of the sky longer and collect more photons, you find even more galaxies. In fact, the latest estimate, and this has changed since I was in school, it keeps getting larger. The latest estimate is that in the visible universe, because there is part of the universe that is not accessible to us, there are perhaps 2 trillion galaxies. Multiply that by 100 to 400 billion stars, and you can just knock yourself out. Now, I'm actually going to skip over the next few slides. This is about the great debate, which was discussing whether the universe existed in our galaxy alone or other galaxies, and we are going to talk about that next week. So I'm going to skip through these and go right to the man. This is Edwin Hubble. And Edwin Hubble in the 1920s was looking at the Andromeda galaxy through the Hooker reflector. This is the largest telescope of the time, a 100-inch primary mirror on Mount Wilson, I believe. And he was looking at this, which at the time was not the Andromeda galaxy. It was called the Andromeda Nebula, because again, we didn't know if there were other galaxies back in the early 1920s. And he noticed something very interesting. He noticed that there was a star, a special kind of star. There's a Hooker reflector. Just for your, I've actually been there, and I think I probably sat in a chair that Hubble sat in. It was just so wow. Exciting. They still have the old furniture in there. So they had to drag me out. I was half conscious after that. It's just amazing. And here's a picture of the Andromeda Nebula. This is actually taken from an old book that called it a nebula rather than a galaxy. And he noticed in the Andromeda Nebula, let me go back here, that one of the stars was blinking on and off. And he knew what that meant. This was a very special kind of star that he found called a Cepheid variable, which is one of the stars that we use as what are called standard candles for measuring the distance to galaxies. Enter Henrietta Leavitt, who was observing a special Cepheid star called Delta Cephei, and noticed it blinking. And Leavitt figured out that the rate of the blinking of this star, the brightening and dimming of the star, was related to its absolute magnitude. This is a remarkable discovery, because it means if you see a star like this in a distant galaxy, and you can simply measure the period of its brightening and dimming, then you know its absolute magnitude, its absolute brightness, and from that you can get its distance by observing how dim it looks. This is called the period luminosity relationship for Cepheid variable stars, and it's remarkably constant. Some of the stars are larger, and so they blink slower. Some are smaller, and so they get brighter and dimmer more quickly in a matter of just a few days. But here's that relationship, and you can see that all of these data points here lie pretty close to a straight line. So if you know for Cepheid variables, out to about, I don't know, maybe some tens of megaparsecs or something, you can see them. If you know its period of brightening, you know its absolute magnitude, and therefore, by observing how dim it is, you know how far away it is. So that's one method of determining how far a galaxy is. Find a Cepheid variable in the galaxy, and you know the distance to the galaxy. But this only works out so far because Cepheids are only so bright. There's another type of standard candle called a type 1a supernova. These are binary star systems that can be used to determine the distance to galaxies as well. And in these star systems, you have a white dwarf that's pulling material off of a nearby companion star. And at some point, when the mass of the white dwarf reaches a limit, which happens to be 1.4 solar masses, this is called the Chandrasekhar limit, the star has enough mass so that it triggers a runaway nuclear reaction, and you have a supernova. And these supernovas are remarkably similar in brightness. And so if we can find these type 1a supernovas in distant galaxies, again, we can know how far away they are. So Hubble was observing this delta Cepheid, this Cepheid variable star in Andromeda, and he was able to determine that the Andromeda galaxy was, at the time, was felt an enormous distance away, something like, I think his number was around 50 million light years. Let's see, the Andromeda galaxy is about 2 million light years away, so I think it was about a quarter of that. But he was able to show that it is quite far away. But he also noticed something else about these galaxies. He noticed that most of them were moving away from us. And he was able to determine this by observing the shift in the frequencies of the spectral lines for those galaxies. And this is the Doppler effect, right? The Doppler effect, it works with sound, it works with light, it works with galaxies. And by measuring the shift in known spectral lines, and you can see the equation for it up here on the upper right if you're interested, you can get the velocity of recession of the galaxy as a function of the speed of light. So we have distance to galaxies. Now we have velocities of galaxies. And here you see an example. On the bottom, we have a laboratory reference spectrum. So it's not moving with respect to us. It's sitting in a laboratory on the Earth. A nearby star, which is moving a little bit, but not very much with respect to us. It's in our galaxy. And then successively further, as we move up, successively further away galaxies. And so you notice that these galaxies are moving faster away from us as they get further from us. And this was the remarkable set of discoveries that Hubble made. And he plotted these. This is his original data. This is his original 1929 plot of galaxy velocities on the left and distances on the bottom. And he drew a couple of lines in them, and he said, hey, they look kind of pretty like there's a linear relationship here. Just thinking about it. Now, our good audience will notice that there's a couple of things wrong with this plot. First of all, on the y-axis, these are velocities. So these are kilometers per second, not kilometers. So he didn't label it correctly, but he understood what he was trying to do. On the bottom, the actual distances were miscued. And so they were off by about a factor of 8. Okay. So if you take this graphic and you look at the slope of the line that is generated, the best line of best fit through all these galaxy data points, the slope of that line is something called the Hubble constant. And in this case, for the data that Hubble had, even if incorrectly observed, he thought that the universe was about 2 billion years old. Well, how does he do that? The slope of the Hubble constant is y over x, kilometers per second per megaparsec, right? Those are the units. And kilometers per second, well, kilometers is a distance, seconds is a time, over megaparsecs, well, that's a distance. So you have distance over distance, which is 1 over time. And that time is the age of the universe in seconds. So 1 over the Hubble constant, which is written as h with a 0 below it, is the age of the universe, provided you are able to work with the same distance measures. And I have an example here, just to prove my point. So if we take an example of type 1a supernovas for distance, they produce a slope of that line of 72.8 kilometers per second per megaparsec. And as we just said, that is 1 over time. So if we take 1 over that, we get time. And that number is a meaningless number, 0.01374. And that number is meaningless because we're using 2 different distance measures. We're using kilometers for kilometers per second and megaparsecs for distance. So we have to convert. And if we multiply this number by the numbers of kilometers in a megaparsec, we get an equally indistinguishable number of 4.239 times 10 to the 17th seconds, which is, in this case, the age of the universe given this model. So I went ahead and divided by 60 seconds in a minute and 60 minutes in an hour and 24 hours in a day and 365 days in a year and a billion years. And we come out with a reasonable number, 13.4 billion years as the age of the universe. Now, we won't talk too much about this time, but there are different derivations for this magical number, the Hubble constant. And depending upon whether you use Cepheid variables, type 1a supernova, or you can even get this value by looking very carefully at the cosmic microwave background radiation. But over the years, the value of the Hubble constant has gotten more constrained and more constrained. And even though there's a little variation in it now called the Hubble tension, which we'll talk about next week, we're kind of centering on a value that's kind of in the high 60s, low 70s, kilometers per second per megaparsec. And the reason that this number is important, again, or one reason that it's important, is that from it you can derive the age of the universe. And we will get into all of this, the age of the universe, the size of the universe, dark matter, dark energy, and all of the other craziness of the universe related to its formation and evolution next week.
Fantastic. Great. Thank you very much, Lou. And yes, next week we will be delving into all of these weird and wonderful things. And we hope you can join us for that next week. Let me just get rid of this off the screen. And there we are. So next week, oh, hang on, my camera's gone off for some reason. Next week, we will be looking at all of those things. We'll also be talking about the great debate, which Lou mentioned earlier. We're going to have some fun with that. Right now, though, we'd like to thank you for staying with us this far for our look at galaxies tonight. Just a couple of things before we move on. Firstly, the current edition of Capcom magazine is now out, and you can subscribe to it by going to the SpaceOddities YouTube channel here. And it's a monthly, a bi-monthly magazine, comes out every 2 months, produced by Michael, about rocketry and spaceflight, and he's been doing it for a couple of decades now. It's a free magazine in the form of a PDF file that you can get sent to you by simply sending an email to Capcom, CAPCOM, at spaceoddities.space, put subscribe in the title, and you will receive the next available issue. So, Michael, what's in the current issue?
The latest one is a picture on the front of the from the Fram 2 flight. Nice,
the polar flight.
Nice image of the an astronaut with his laptop in the window, in the cupola window of the Dragon. Very, very 2001. You know. So yeah, it's just quite a few different news stories this time. Yeah, but I'm hoping that for the next issue, the July issue, it will be the 50th anniversary of the Apollo Soyuz mission.
Right.
So I'm hoping to do a few things about that for that issue. Yeah.
God, 50 years, eh? Where did that time go?
I know. Yeah. So,
I remember it as if it were yesterday.
Yes. Don't we all?
Okay, the other thing is, while we're talking about galaxies, we did produce a video as part of our Astronomy Basics series called What is a Galaxy? And if you go to the SpaceOddities channel and open the Astronomy Basics playlist, you will see that along with what is the sun, what's a magnetar, what's a pulsar, what's a neutron star, what's the recipe for life, etc., there is a video there called What is a Galaxy that will tell you basically what it says. It does what it says on the tin. It's about what exactly is a galaxy.
It's called.
So there we are. So we hope you will visit that and the other playlists on the SpaceOddities channel. We've now put well over, I think now 500 videos on the SpaceOddities channel. So do go and have a browse through the playlists, and we hope you enjoy the videos, basically. So there we are. Just to let you know that in 2 weeks, we will be celebrating the 3rd anniversary of SpaceOddities.
Wow.
Yeah. I can't believe we've been doing this for 3 years, but that's coming up in two weeks, more or less. So the week after next, we will be doing something to celebrate our 3 years. We hope you will join us for that. Obviously, we'd like to say an enormous thank you to all of our viewers, because we couldn't have stayed as long as we have on YouTube without you. So we'd like to say thank you to you for that. And we don't know what we're going to do to celebrate it yet, but we'll work something out for you. So we got that
Cake.
Can we have a pint?
Cake.
Can we have a pint for the show?
Yes, we can have a virtual drink.
3 candles on the cake.
Yeah, we got to have a cake, definitely. Who's gonna bake the cake? I'm not much good at that sort of thing.
I'll do it.
Oh, okay. There we are. Roger's going to bake a cake
Hey.
for the 3rd anniversary celebration.
Yay!
We're very happy to still be
Got the candles.
going after 3 years.
Yeah.
When we started Space Oddities, after we'd all left Astro Radio when sadly it closed, we had no idea how long Space Oddities would last, but believe it or not, we've now gone for 3 years. So you get less fun. So there we are. So join us for the 3rd anniversary celebrations of Space Oddities the week after next. Usual time on a Tuesday, 8 o'clock UK time. In a little while, Roger is going to be giving us this week's fanfare Constellation of the Week. But before we do that, yes, Daz.
Before we actually leave Galaxies, can I just make a quick clarification of something that I said? If I can just share my screen again, I will just endeavor to go back. I just want to clarify something because I got myself in a bit of a muddle, and it was this image here. And I was talking about that some people see this as an evolution of galaxies, and what they thought was that the left-hand side are the early galaxies, and then the spiral galaxies are the later galaxies. Well, of course, and so they saw this as an evolutionary path. This is how things have evolved over the eons. But of course, we now know, thanks to James Webb, that the early galaxy was swamped with spiral galaxies. So this isn't, like I say, an evolutionary tree. These, if anything, it's the other way around. These galaxies are possibly the earlier galaxies, and they've been disrupted by interactions with other galaxies. That's why they're sort of like diffused as they are. So I just wanted to make sure everybody understood that. And other thing, you mentioned the Magellanic Clouds, and one thing I was going to say is that the Magellanic Cloud is classified as an irregular galaxy because it's in a bit of a mess. But recently, due to more observations with different facilities and telescopes and things like that, they think they have actually detected that it does have a spiral structure.
Really?
So yes, it was again, as I said, this and this goes back to what Paul said going back a long time ago in the chat, that it's surprising what you get wrong until you get all the data. The more data you get, they realise that things are different. So yeah, that just sums it all up. Because I mean, again with the Magellanic Cloud, we're supposed to merge with that before we actually merge with
Andromeda.
the Andromeda Galaxy. So I just thought I wanted to make sure everybody understood that.
Right.
Get myself a medal there. So thanks for that.
Fantastic. Andy. Thank you. Okay. So as I said, Constellation of the Week is coming up. But before we get to Constellation of the Week, yes, it's that time again. It's that time when we delve into the lunacy on social media, otherwise known as Einstein of the Week, where we show you some of the quite surprising and often completely freaky comments that people post on social media. So without more ado, let's go to Einstein of the Week. Give me 1 second. So this I've only got 2 entries or 2 contenders for Einstein of the Week this week, but I think you'll enjoy these. So Einstein of the Week, the first one is a comment left on Facebook by somebody who was commenting on this beautiful image of M51, the famous pinwheel galaxy. It's funny, we're still on galaxies, and this was coincidental. So, I mean, what could you say about this beautiful image? It's a beautiful image, and you know, it's, whoever took it is very clever, and all the rest of it. This person had other ideas about M51 though, and this was it. M51 is 69, 666189, sexology, hybrids, humans, knowledge X reproductions, or knowledge times reproductions, maybe, I don't know, reptilian aliens, mermaids, ants, humanoids, jellyfish humanoids, ETC clonine, G ghost, devils want to be the holy probably, spirits, Ashod, hog, H1N1, HN51, M51 makes H5N1. If aliens can make these hybrids, is it that hard to make viruses, RNA encapsulated with humans' DNA, proteins? Then they have all the scientists, the greatest minds. Have you all believed that is nature produced? Wise. Is that wise they put a loads of them right at the times they have you all believed overpopulation? BS.
Oh,
I think somebody missed the medication trolley.
what was that all about?
That is absolute. Well, it is.
Yeah.
Well, you know.
I mean,
And the worrying thing is this person's can probably vote.
Yeah. Yeah.
Well, it's a bit worrisome that it makes sense to them.
yes, yes, that is worrying. Yeah. I have. Well, I don't suppose any of us have any idea exactly what they're trying to say, of course, but it's something to do with aliens and reptilian aliens and I don't know what it's all about. Anyway, so that was number 2.
I think it's
like
somebody who believes. I think it's somebody who believes in Mond.
Hey,
Yeah.
Yeah.
It's got all the hallmarks of a Mond believer. It definitely does.
Oh,
Yeah.
I can't wait till the debate. I can't wait.
Lou, we need to schedule the dark matter versus Mond debate in. We've been talking about it for long enough. So
Agreed.
we ought to schedule that in soon. Okay. So a bit long-winded as well, but if you thought that was long-winded, you ain't seen nothing yet. So here's this week's Einstein of the Week. And the only title that one could give this is Breathe. For God's sake, breathe. So here we go.
What?
All right, I'm going to read this. I'm going to go for this, guys, because there might be people in the audience who can't see this. So I'm going to read it out.
May the force
Light
be with
speed
you.
limit is relative to everything that can be seen within the light we see because it moves at a pace with all other visible objects in sight. As far as we can see in the universe, where all objects in light's view are moving within each other's inertia at a speed where light is possible to be seen and can keep up with it all, because even in space we're still just being launched in motion with everything. Because we just came off something that was moving with that speed at a speed to keep up with it, still like jumping from one river stream to one that's compatible of speed to transfer, but not completely still or too fast to see and join. But there are more than likely objects with inertial movement in uniform with what they can see is above or below a threshold where relative light speed will allow us to see each other because we can't see above light speed, which is why black holes look like nothing, because they are obstructed objects that are both inside and outside the visual inertia zone, creating a protruding structure on the edge of our unit of uniform inertia, but they can see all see everything within their boundary.
Okay. Right.
Well done.
No, don't say anything yet. We haven't finished.
What?
Moving inertia within a speed that light can travel and be seen at the speed they uniformly move with all their other objects. So changing vector of light speed inertia would allow for faster than light travel in our visible uniform inertia's mass or visible universe. Without actually going to the speed of light, you would just escape the uniform motion you have with everything we see by counteracting the forces. Then when you're at an orbit distance from all objects, you'll be able to be not dragged down by the uniform inertia that light is detrimented by, and you'll be able to travel with control toward all visible objects of light from a distance similar to how when looking at a tornado in the orbit of Earth it appears to be not moving or moving slower, but inside its chaotic storm. You'll see the universe moving slow and be able to quickly move to any position within it because you'll be able to move with no limits of speed of light because you're not being held within the current of inertia, velocity, or the other moving objects. You're competing with overacting on each of the other forces to slow each other down, and light will be instantaneous speed because the distance it'll have to travel while moving will not be controlled by forces of motion to escape the universe's inertia. All you have to do is either manipulate absorption of electricity produced by the force energy of its movement by using its gravity to force an exponential increase in escape velocity so that you warp only a small space of inertia in the whole loop of the all uniform masses from its regular state, allowing you to dodge the motion of everything, which wouldn't collide you with everything because you'd refract from everything, similar to how light does, or you use a magnetic field of different operating centrifuging parts, creating the field to create the same experience. I finished.
That's one hell of a sentence, isn't it?
What's that mean?
Well done, Andy.
Thanks.
Yeah, I think you need
Can
a
I
round
please
of
now?
applause for that. But
Did anyone understand that?
Somebody
mean,
get a
you got-
nurse.
yeah, I'll be quite honest. I mean, I don't mean this derogatory to anybody at all, but halfway through that, I wanted to self-harm. It's oh, I mean, do you think you could say that without taking a breath?
No.
Just throwing out there as a challenge.
Yeah. So let's just so it's that and that and that.
That is
There we are.
absolute nonsense.
Where was that from?
That's from Facebook, and it was actually a comment on a post about light speed.
Right.
So
Gonna
there we
say-
are.
If you did break it down into
It'd be,
sentences, would it make sense?
No.
No, I don't. That's what I
I'm
thought.
going to say it would have been way too long for X.
Yeah. Oh yes, it's definitely too long for X. So there you are. I
When I
did
was
reply
at
to
the-
this. I did reply to this person, and ask them very nicely to learn some punctuation and use it. Although actually, no, I wasn't that nice about it. I won't tell you what I said. There might be children watching, but yeah. So there you are. So this is our Einstein of the week this week. So I hope you enjoyed that. As I said, there weren't many this week that I spotted, but I'm sure that there'll be more next week. So there you have it, Einstein of the week.
When I was at the National Space Science Data Center, we often got emails, letters, if you will, from people who would claim that they have found how to travel faster than the speed of light and how to break other, physical laws. And they were quite humorous to read. So maybe we'll try to gather those together for a future show.
Oh, yes.
Eric says it's from Stanley Unwin. It sounds like a Stanley Unwinism. Actually, I wonder if AI could rewrite that as a Stanley Unwinism. I'm going to do that.
Well, I think Paul's answered that.
Yeah. Yeah.
Random word generator.
Random word generator. Well, that's what I thought at first, Paul. But if you read it, it does have some sort of internal logic. So I don't think it's a random word generator. So maybe. Sandra says, "Can you repeat it, please?" Shall I? You want that, Sandra? Or you got it? No, only joking. I'm not going to do that. So there we are. We do have to say happy birthday, happy 60th birthday to Sandra.
All right.
Today. Happy birthday, Sandra.
Happy birthday.
Happy
Hope you
birthday,
had a
Sandra.
fantastic day. And yeah, so it's being 6 is fantastic because, as Paul pointed out, it does give you a license to misbehave. And yeah, Derek says predictive text not working.
Happy second Saturnian birthday, Sandra.
Yes.
Oh, yes.
Indeed. So there we are. All righty. So we're going to move on now to our legendary constellation of the week. So Roger is going to, again, it has a connection with galaxies. And this week I'll let Roger tell you what the constellation of the week is.
All right.
Hey.
Pegasus. Oh. I thought,
Is it not
yeah,
showing?
but we got
I've got Doris. I've got black slides here. Is that?
Well, we got Constellation of the Week Pegasus, which I don't think is correct.
No, we did that last week.
Yeah.
And now we've got
Andromeda, here we are.
I can't see
Oh,
anything.
One of your slides says Andromeda with a lot of text.
Yeah.
Not quite as long as the other one, but yeah.
No.
Oh, I can't see what I'm doing
Oh.
here.
Says
I've got
1 of
nothing.
16.
Oh, okay. Just bear with us, guys, please. We seem to have a technical problem. Let me just see if I can do anything to fix it.
Yeah, it does say Pegasus. I don't know why it's doing that.
Yeah.
Oh, for goodness sake.
Looks. I don't know. No. Will removing it and putting it back make a difference, perhaps?
Turn it on and off.
Oh, dear. Don't know what's going on
No.
here.
How strange.
Well, it says Pegasus, but it is Andromeda actually.
So Andromeda is our constellation of the week.
Yeah, it's just got the wrong title slide on. That's
Yeah.
all. Okay.
If you just, but you can't see it, no?
I'm not getting anything on mine.
Oh, that's weird.
Anyway. I've got the present, so you can see it and I
Yeah,
can't.
yeah, yeah.
Is that right? Okay, well, I'll go through the slides and I'll click my PowerPoint so I know what I'm looking at.
Okay.
Right. Okay, so number 2. So we've got slide saying Andromeda is one of the 48 constellations listed by the 2nd century Greek Roman astronomer Ptolemy.
That's
Is that
correct.
right?
Yep.
Oh, right. So it's one of the 88 current constellations that we now are associated with now. So it's named after Andromeda, daughter of Cassiopeia, and in Greek myth, who was chained to a rock to be eaten by the sea monster Cetus. So we've all got all of that. So Andromeda is normally visible only north of the 40-degree latitude. So anything else, it will not be visible. So onwards to the next slide. So, okay. Ooh, hang on. Ooh. So we've got a listing of the names of the stars, and we've also got some interesting objects. Obviously, everyone knows the Andromeda Galaxy, which also has Messier 31 and 32 with it, M110. But there are a lot of galaxies in that constellation, and also some open clusters. So we will go through some of those for this presentation. So number 4, right? Okay. So Alpha Andromeda, which is the top left star of the square of Pegasus, is called Alpheratz, brightest star of the constellation, and is a AOP class binary star of 2.1 magnitude. And although its star's traditional Arabic name Alpheratz and Sirrah come from the phrase Sirrah al-Faras, referring to the navel of the
course
horse.
It does.
Yes, because it's part
Yes.
of Pegasus. And that's also part of the square. So we've got Alpha Pegasus, Beta Kappa, and Pegasus as well. So there we go. Right, so onwards with slide 5. Beta Pegasus is also known as Mirac. It's a red-hued giant star and is part of the asterism known as the Girdle, as you might see from the outline of the drawing over on the right-hand side.
Very imaginative,
And
these
as we
people,
go
weren't
on,
they?
I know they can be very, very thoughtful. And then Gamma Andromeda is Almac, and that is, oh, I haven't got that labeled right, and that's sort of leading through the constellation to where M31 is. So we'll crack on with that, and then we go on to number 6 and then number 7. So that's Almac there, and then we go to 7. So we're going over to orange giant star, which is Delta Gara, down amongst the constellations there, leading through magnitude 3.3, number 8. Right. So we've got a little group known as Frederick's Glory. I don't know how many of the group know about this little asterism.
No, I never heard of it.
It's Kappa, Lambda, and Omega, or whatever O is. So that was from a former constellation by Federici Honores, probably Spanish or something. And they've got quite a few different stars and distances there from that. But we're basically going on to the Andromeda Galaxy, so M31 or NGC 224. And as we all know, it's 2.5 million light years away, gradually heading towards us in our direction. So in about 4 billion years, we will gradually merge together, which will be quite interesting. So it'll be a double whammy of our sun dying and then the merging of the Andromeda Galaxy with us as well. So that will be a photo opportunity, I'm sure, for anyone that might want to be here
I hate
that
when
long.
that happens.
Yeah. So this is the earliest picture taking of the taking in 1888, I believe.
Did you take
Yes,
that, Roger?
29th
Is that
of
one of yours?
December. No. No, it's quite interesting because it was done with a 20-inch reflector, but the tracking scope was a 7-inch refractor. So you know that was quite a interesting combination to use. And this was taking in Liverpool, taking over 4 hours of exposure because photographic plates in those days were very, very slow. So it's probably something like 5 or 10 ISO, I would think.
I mean, that was
But,
Mr. Grubb. Wasn't he one of the firemen off of Camberwick Green? Huge.
No. This is
Cuthbert, Gibble, and Grubb.
No, this is Isaac. Yeah, taken. Yeah, the telescope was made by Harold Grubb of Dublin, but this was Isaac Roberts that was the actual photographer.
And then become a fireman on Camberwick Green.
Yes, that's right. Okay,
you watch far too much TV, does.
Yeah. And here's a couple of more modern images. Mine's the one on the left, which is a closer view of the bottom part of the Andromeda Galaxy. And then the other one over on the right-hand side was done by a friend of mine. And he's obviously put the hydrogen alpha in to highlight some of the interesting regions around the galaxy there.
Very nice.
Fantastic. Lovely image, Roger.
Yeah. Yeah, I know.
I mean, looking at that image and the one taken in 1888, you can see the huge amount of change since then, can't you?
Absolutely, yeah, it's amazing.
But of course, like we said, we've been talking about M31 and that we're going to collide with it. Well, the collision has already started because apparently the halos are already intermingling with each other because around each galaxy there is a big halo of dust and gas, and they've started to actually interact with each other. So the collision has started. Seatbelts only.
Right. Okay, so we've got also another interesting object further over, and this is NGC 7662 or Caldwell 22. It's given also the name of the Blue Snowball Nebula, and apparently it's quite a popular target for amateur astronomers. So I've yet to capture this, and you will see a better view of it in the next slide.
Oh wow!
Obviously, taken with the Hubble. But,
I've never seen that before.
I will have a. No, well, I might have. We'll have to give it a go. I've not seen this one
That's
before.
a Hubble image. I reckon a sea star will bring that out a bit more.
Yeah, maybe.
Yeah, maybe.
We'll get Lee Hoare on that one. He likes doing things like that.
Yeah,
beautiful, isn't it? It's lovely though.
Beautiful.
Yeah,
it's up to its name.
Yeah, certainly does. And then we've got an open cluster, which will be this one, which is Caldwell 28 or NGC 752, a little open cluster. And this is the image of that. Not very exciting open clusters. I find the globular clusters a lot more interesting, but there we go.
Yeah, well, you've got the Hyades, haven't you? Cluster, which
I mean,
is
you got the
now,
Persepe as well.
which they're now saying that is now so it's so open now that the designation of cluster may disappear. Because of course, like you say, the globular clusters are always the stars of the show. But it's a shame. You can see there's definitely a group of stars there, but they are really spread apart now. So yeah, fine.
Yeah. Anyway, that concludes my little brief synopsis of the constellation of Andromeda.
Thank you very much, Roger. Fantastic, lovely stuff.
Okay.
Okay, so let's just get rid of.
Yeah, I hope to have brought some other objects to the minds of other astronomers to think about, rather than just M31.
You're gonna have to have a look at that snow.
Yeah, no, there's some interesting objects there that I was not aware of. So there we are.
Yes.
Just want to go through a couple of comments here that people have left. Louis, you still there?
Yep, I'm here.
Okay. Yeah, kudos to you, Lou, because Anne says, I think that's the clearest explanation I've ever seen. Lou, thank you. So there you are. And Paul equally says, thanks, Lou, very interesting.
But how many people try to explain the Hubble constant to you? I mean,
well, exactly.
Be a very small data set.
Every day.
Yeah. The man in my local butcher was trying to explain it to me only this morning.
Yeah.
And he didn't do a very good job, unfortunately. But there we are. So yeah, thanks for that. Thank you for that, Paul. And what else did I see on there? Stuart says lots of information to take on board. Very interesting. Thank you, which is great. Thank you, Stuart, for that. And we do like it when people say nice things about us. We're only human. So there we are. And yeah. Paul says the collision between our galaxy and Andromeda has already started. And he also says, hang on, where's it gone? I lost it for a moment. Okay. He says, thanks for letting him know. Luckily, my car is equipped with airbags. So good. Yep, fantastic. So there we are. Lou, you might know something more about this than I would. So if we've got two galactic halos that are now in collision, I was thinking, depending maybe on the temperature of the gas, is that going to result in anything visual flaring up? Would it?
Well, in general, galactic collisions result in an enormous amount of star formation. Okay?
Yeah.
Nothing is actually, I mean, it would be very, very rare for anything to actually collide because the distance between stars is so great. But the gravity from the two galaxies is pushing and pulling. And so this gas gets compressed and that starts star formation going. So these galaxies are often called starburst galaxies or superluminous galaxies because stars are being formed like crazy. Now, what that does is, yes, forms new stars and new solar systems, but it also depletes the interstellar gas, which is why, as I think Daz was saying, these elliptical galaxies are tend to be very gas poor. As far as the halos interacting, I guess it would depend on the density and whether you're going to get any kind of star formation or any kind of heating as a result of friction from formation of
that's what I was thinking.
clumps. I don't know.
No, interesting. I was just wondering whether, we might not now, obviously, but in a few million years, start to see something between us and the Andromeda galaxy happening. So
yeah, I think the halos are so diffuse, though they actually exist. They are, and I think they're I was just trying to think. There was something about intergalactic gas. I can't remember what that was about. But yeah, it exists. And usually it's like I say, you got the halos around the galaxies. But I think it's so diffuse at the moment. Maybe, like you say, a bit down the line when we get into the thicker stuff, maybe something. There's bound to be something that's going to start kicking off, because once you get the two actual outer rings starting to come into each other, you're going to have lots of gas, lots of swirling, lots of gravity interaction. That something's got to start to kick off, and of course we know that they're going to pass through each other. Then they'll turn over the next, I don't know, never probably 4 billion years, move away from each other, and then come back together and pass through each other again. And then you'll end up with like the elliptics. First of all, you go through a stage where the rings will be, the spirals will be disturbed, but they'll possibly keep their shape for a while. But after a while, they'll just become a mangle, and they'll become a massive irregular galaxy.
Yeah.
And so yeah, it's because I mean, if you want to see two galaxies that are actually interacting with each other, the closest we've got are the Magellanic Clouds, because there is a star bridge between the two of them.
Yeah,
they
that's
are
true.
actually, there is a bridge between them. So they are actually interacting with each other, and of course, very soon we're going to be interacting with the Magellanic Clouds themselves as well. So. Interesting stuff.
I think we already have. Is that perhaps the prevailing theory that?
Yeah, I think we have in the past, and that's why they look like they do. But yeah, I mean that was fascinating what you said, Andy, about the stars that we thought were satellites are actually moving towards the galaxy, not just orbiting. That's a fascinating thought. So, yeah.
And
you're talking about baryonic matter halos, right? Because there is a dark matter halo.
Yes, there is. Can I have that in writing for me, Lou? There is a dark matter
halo. Yeah.
I spoke too soon. I'll never hear the end of this.
Perhaps this debate won't be as fiery as we think it will, Lou.
Yeah, we're going to edit that and put it on a loop.
Yeah.
Would you please?
There we are.
An inferred dark matter halo.
Yeah. You're like you're like one of those punks from the 70s who says that all progressive rock music is horrible, but they're avid fans of Genesis and Pink Floyd,
or flat Earth societies around the globe or something.
All right, then. We're going to start winding things up this evening. We would like to thank you, all of you, for being here and all of your comments and contributions. And thank you so much. Happy birthday again, Sandra. I'm a bit disappointed that you're not absolutely pissed, Sandra. So judging by your typing, you're perfectly sober. I don't know, that's a disgraceful behavior for a 60-year-old. So there we are. So so we will be back next week. We're going to delve into galaxies and look at more aspects of galaxies, including a look at what the James Webb Space Telescope is telling us about the earliest galaxies in the universe, and how it's really forcing astronomers to scratch their heads and rejig their models of the early universe. But we'll talk about that next week. And we'll also be doing the Great Debate, reenacting the Great Debate, which we'll tell you all about next week. So that's fun. And as I said, don't forget, in 2 weeks' time, we will be celebrating our 3rd anniversary here on Space Oddities. You could do us all a favor, as always, by liking, subscribing, and then in the comment section on YouTube, not the live chat, but on the comment section, just leave a comment, whatever you want to say, no matter how short, because that really does help us get noticed by the YouTube algorithm, and that will enable the algorithm to recommend our videos to more people if it sees that the actual content of our videos are being discussed in the comments. So if you could do that for us, we'd be very grateful, because it does really help us. And lovely to have you in the audience, as it were. Hope you and Mick are both well. Hope to see you very soon. And there we are. Sandra doesn't drink. How have we ended up with somebody in our audience that doesn't drink. Who let her in? For goodness sake, disgraceful behavior.
Our good fortune.
Yeah, our good fortune, of course. Of course.
And I have it right here. Sorry, a paper from Gates et al. On the local halo density, 1995 Astrophysical Journal. The local halo density is estimated between 2 times 10 to the minus 25th grams per cubic centimeter to 10 times 10 to the minus 25th. So there you go.
There you are.
How many teaspoons is that?
Pretty darn low. Is
Pretty darn low. But it is happening. The collision between the Milky Way and Andromeda has started.
I want that in teaspoons, Lou.
Wait, just give me an hour.
Can I have it in moles?
You can all have it the way you want it. I'll just give you a minute.
Okay. So there we are. So thank you again, all of you, for being here. We'll see you next week. Usual time. Same bat time, same bat channel. Space Oddities, Tuesday nights. What else have you got to do on Tuesday nights? Be honest. So we'll see you at 8 o'clock UK time next week. And have a fantastic week, everybody. And thank you for being here. So from all of us at Space Oddities, we hope you enjoyed the show.